Professor Hwa A. He is Professor of Bioinformatics, California State University, USA. He initiated a conference series, Bioinformatics and Genome Research, the very first international bioinformatics conference in 1990, and is still ongoing. He coined the word of bioinformatics and initiated the country way to create a field of bioinformatics. This effort earned him the invited the father of the bioinformatics. Ghaffar, please.
Thank you so much. I'd like to switch gear a little bit. Professor Mullah was talking a lot about wet lab. So what I'm going to do is to take you away from the wet lab and go into silicon lab. That means I'll be talking to you about computational approaches. Okay? Professor Miller actually makes me very envious. He has been to 60 countries. The problem with my work is usually when I go into cyberspace, I don't know where I am. But in any event, I know right now I'm in Egypt, and I'm at the National Research Council because this morning we had a very nice introduction of the facility and a very impressive, extensive research work going on at the National Research Council. I'm sure I'm in the right place. So today what I'm going to talk to you about is, biodata behind big and open data. The reason I'm going to talk about this is because actually there are a lot of data out there in different computer networks that all researchers can actually go out and scoop and do very good scientific work, or even in businesses. So, the Library of Alexandria was the first time humanity attempted to bring the sum total of knowledge together in one place. I had the honor to be in that place 9 years ago, or 8 years ago, I forgot. So that was in 2009, and this is how the Library of Alexandria was started, actually something like 2,000 years ago. Now what we do is we have Wikipedia, and it imagines a world in which every single person on the planet has free access to the sum total of human knowledge. And the word I want to emphasize here is the word free. And that's what I'll be talking to you about, free data. And because of this, you are going to see here, we are treating data, especially those open ones, those free ones, as nutrients, food for machine, that is for the computer. How does this come about? This came about because of integrated circuits in the 1970s. And Professor Jack Kilby was the one who invented integrated circuits. He's the oldest person among the three of us, and he deservedly won the 2000 Nobel Prize in Physics. So that was in the 1970s. And because of Moore's law, you are going to see the computer capacities have actually increased drastically over the last quarter of a century, or over the last half a century since the information technology started. So, last year, when I was at a Fortune 500 forum, I made this statement. Everything that can have a chip in it will have a chip in it. And nearly everything with a chip in it will become a node in humanity's ever-growing big database. And this is happening right now. So you are going to see, and therefore you hear a lot of people talk about personalized medicine, precision medicine is now going through a revolution that is unfolding at this very moment. And this is not only true for personalized medicine, it's also true for other professions, the vets, hydrobiologists, agriculturalists, and other researchers. And this is what we have. We are beginning to tag cattle, even pets. And this is something like in the year 2000 when I visited one of the largest sequencing centers in the world. And I want you to look at the machine, how big the machine is. And that was the most powerful machine in the year 2000. And compared to now, this is a sequencing machine that we had, and there's 7 generations afterwards. When I say 7 generations, I don't mean human generations, I mean computer generations. So scientists can now actually employ sequencers smaller than a deck of cards. They will plug directly into a laptop through USB port. So they can be taken out into the field to sequence the genomes of animals and plants, and maybe even viruses of Professor Muller. So because of all this, you're going to see that now people are talking about data as new oil. And for me, I call it the new soil because that's what I'm going to plan my research on. So people are created equal. Computers are not. In the past, power and influence were gained by controlling something that people wanted. For example, oil or transportation routes. But now, to be powerful, you have to have information superiority as computed by the most efficient computers on the network. Also, because of this, what you're going to see is you're going to hear a lot of people talk about data, and they come in many different forms. You probably have heard about smart data, which actually refers to increasing common pattern emerging in the big data scene involving the productization and wealth creation of persistent data through predictive analytics. So this is primarily for businesses. You probably have heard a lot about deep data, a lot about fast data, about big data. And then after I submitted the abstract for this particular conference, I saw this particular book at a bookstore in the United States, and it went on sale. And it was published in 2016. So I almost had to change my top title as small data, but I didn't. Because actually the book is talking about just looking for clues in data. What I'm going to talk to you about today is open data. By open, I mean free, or something that's reusable. So what's the difference between all these different forms of data? They are actually just a matter of semantics. So here I would like to compare and contrast the 2 different data forms. One is big, and the other is open. Open data can best be described as accessible public data that people, companies, and organizations can use to launch new ventures, analyze patterns and trends, make data-driven decisions, and solve complex problems. It's different from big data, although the 2 overlap. Here I'll show you a Venn diagram. So you're going to see, to the left here, we have non-public data for marketing and for businesses and for national security. And down here, we are going to have some form of business data that has got to be reported and put in the public domain because it's required by the law of different countries. And here, we also have government data. How do I go back? I claim that I work with computers all the time and I don't know how to operate a computer. So you're going to see also here in open data itself, it includes actually large data sets from scientific research and social media and other government sources itself. And here also some data sets here, right in the middle here, something that I want to talk about. And these are the data set that, open data set that people talk about all the time, the weather data, the GPS data, and healthcare data that are all made public for everybody to use. And they are free, and they are reusable. So, open data is the world's largest free resource. It's unprecedented access to thousands of databases, and is one of the most revolutionary developments since the information age began. And it combines 2 major trends. First, the exponential growth of digital data and the emerging culture of disclosure and transparencies, and especially scientific research. As of late, you probably have heard about the former president of the United States actually threw out a lot of data, make a lot of data public. And a lot of companies, especially for people like me from the Silicon Valley of California, a lot of new companies spinning out actually precisely just doing, writing all sorts of apps for these different data sources. So it's at this moment in time that it gives, the open data gives individuals, researchers, and business full access to information that has never been available to the average person. So here I like to read that, unlike most big data, open data is transparent, accessible, and reusable. And that's the word I want to emphasize, reusable in ways that gives you the power to transform businesses, government, and society, and accelerate research and discovery. So here I'll go on and give you 1 or 2 or 3 examples before I quit. So national weather data is something, and GPS data. On top of that, if you put GPS data, is something that people talk a lot about, and you can apply in agriculture. And you also have the census data, data collected by Security Exchange, and others. And then we also have non-government research has also produced large amount of data, particularly in biomedicine, genetics, and so forth. And that is now being shared openly to accelerate the pace of research. So I want to give you the first example of Farm Challenge itself. Farmers, I don't know about the statistics here in Egypt, but farmers in the United States generate about $500 billion a year in revenue, and they make about $100 billion a year in operating costs, in operating profit. So farming itself is a 20% margin business on average. So the one source of variability for revenue nowadays is the weather, because all the other risks of farming have largely been eliminated through herbicide, fungicide, and insecticide technologies. So weather can be a very large driver for outcomes in farming. So farmers can end up losing everything when the weather is not cooperating. Slight variations in weather can cause significant losses in profit. So even in countries like in the United States itself, where there are insurances for farmers, sometimes farmers can be significantly underinsured. So this is a map of California. If you want to know where I come from, it's somewhere close by here, I think. Yeah, that is the Santa Cruz here, and somewhere here in San Jose. So if you are not familiar with the map of California itself, 2 months ago there was a big fire. I was only 100 miles away, and it was a close call. We don't want the 6th largest economy in the world to be on fire. So farmers do not really care about how much rain falls. What farmers care about is really how much water is in the ground itself, which actually is determined by both rainfall and the soil. So if you take 2 data sets together, so here we'll offer a solution for crop yield by incorporating several public databases, including GPS databases, weather databases. The Climate Corporation was originally started to sell a better type of weather insurance, but it has now grown into a company that could help farmers around the world to adapt to climate change, increase their crop yield, and become part of new green revolution. And this is what it does. On a daily basis, the company will tell farmers what field to work on, what field should be spraying, should have spraying or planting done, or what field is at a growth stage where farmers should fertilize, where farmers should wait for 5 days before they start planting, for example. So the goal of this particular software is to predict for the farmers so that they can increase their profitability by 20 to 30%. And this is a huge increase for this particular type of business. Now, the business itself, earlier I was telling you, is not only that it's a business you can use, but you can actually duplicate and reintroduce it somewhere else. The US government satellite does not stop at the border. It covers the entire planet. And the same software can actually be used in Australia, for example, because Australia has their own relevant data. And ultimately, even corn farmers in Africa itself can start get services delivered through their iPhones, or even text messaging services. They will tell them on a daily basis what is optimal time to do, and it's a form of Green Revolution 2.0. And I strongly believe that Egypt itself also has some form of data of its own, and the same software can actually be applied here in Egypt itself to improve the productivity and profitability of the farmers in Egypt. Now let's take a closer look at this particular example itself. Okay, so what has happened for this software to be so successful, to be able to be used internationally? First, you have to take a capitalist incentive way to make things work. In the government, things are slightly different. The government does not like to fail, so the goal is to take not as much risk. But you have to go outside the government to use the capitalist economic model that says take risks and make things work. So a lot of this software sometimes don't make good predictions, but successful ones would actually make you a lot of money. But having said this, it's not quite fair for the government. But without the government support, none of this innovation could have happened. The government is the one providing the infrastructure. For example, the weather data itself came from the government, came from NASA, came from the other agencies, US government agencies itself, and they are now out there for free. Now, if you look at this from another perspective and ask yourself, with the computer technology that I showed you on the second slide, handling of data itself is not a big data issue now. It's an issue of digitization challenge. Any organization can handle it and store big data. There's simply a matter of scaling. If you have more data to store, you just have more storage machines. The real challenge is to make sense out of the data itself. Companies and organizations would have to become digital, to remove the data silos, to make most out of the information. This implies to all sectors, including those people who are actually doing research. And here's the particular model that I gave to you. So you're going to see in the lower half here, there's a loop here. You have a lot of data here. You have access to some free data, open data. So what are you going to do? You are going to forage to see if the data is useful for you or not. So sometimes the data may not be deep enough. So you might have to put another layer of data on it. Like for example, the weather example that I was giving you uses the weather data itself and GPS data. So with the overlap of the two sets of data, the whole thing became useful. But if had you used only the weather data, it probably would not be so useful. Or had you used the GPS data, it probably wouldn't be that useful either. So you have to forage in the very beginning here, in the lower loop. And then if something, you find that there's something happening here, you have some evidence of something useful. So you form a schema. So you go further up, and then you build a case and make hypothesis. And if the hypothesis works, then you know something works. If not, you just have to keep looking around and keep trying. And that's what computers are good for. They will do brute force work for you, much better than a lot of people in the wet lab, where you have to stay there all the time. The computer can crank when you are asleep. Actually, while I'm giving lecture here, my computer's background actually working for me. Now, I want to give you another example. For example, if you look at the food chain itself, there are three principal food chains that sustain us today. The industrial food chain, the organic food chain, and the hunter-gatherer food chain. They might be very different, but all the three food chains are systems for doing more or less the same thing, linking us through what we eat to the fertility of the earth and the energy of the sun. So the ecology teaches us that all lives on earth can be viewed as competition among species for the solar energy captured by green plants and stored in the form of complex carbon molecules. A food chain is just a system of passing those calories onto species that lack the plant's unique ability to synthesize from sunlight. So there's myself sitting there, so you can see I can eat greens, or I can eat a chicken which feed on grains, or I can eat fish which actually feed on algae. And I know there's a very big algae institute which is actually quite new, because 8 years ago when I was here, the institute wasn't here yet. So this is what the food chain is. So if you look at the food chain itself, every edible item in a supermarket is a link in the food chain that begins with a particular plant growing in a specific patch of soil or a stretch of water or sea somewhere on earth. I've already spoken to you about farmers. Now let's look at the other, a stretch of water. And this is precisely what you do. There's an Institute of Hydrobiology here, which is actually a study of water populations, their interactions with habitat, the significance for the transformation of energy and matter, and the biological productivity of the ocean, sea, and inland water. And I have to throw you this equation because hydrobiology is actually equal to oceanography plus limnology. Lim is my name. It has nothing to do with me. So here is just a map of Papua solutions. So it starts with feed. So essentially what you try to do is that what Professor Muller was talking about. He was actually studying some form of diseases here. But my specialty area is in genetics and in bioinformatics. What I care more about is the growth. But the bottom line is just to increase the yield, to increase the uniformity, and then to decrease the mobility, and then to decrease the food intake itself. So that's what you want to do. So at about 3:30 today, actually, I'll be chairing a session which will have a lot of very interesting talk in this particular area. So that's all I want to show you. But there are data out there that you can actually use to come up with some solutions for aquaculture itself. Now, I want to talk to you about actually an American supermarket. It turns out to rest remarkably narrow on biological foundations comprised of a tiny group of plants that's dominated by one single species, is corn. Corn is what feeds the steer that becomes the steak. Corn is what feeds the chicken, the pig, the turkey, and the lamb, the catfish, the tilapia, and increasingly even the salmon. A carnivore by nature that fish farmers are re-engineering to tolerate corn. The reason I mention this is because I'm in genetics myself. And corn is also what eggs are made for. And a few days ago, I was walking down the Tahiri Bridge, and this is what I saw. So this is also very popular in Egypt itself. So corn is actually very good because it's a C4 plant. Few plants can manufacture quite as much organic matter or calories from the same quantity of sunlight and water and basic elements as corn. 97% of what corn is comes from the air, only 3% from the ground. It's a good source of food for human beings. The problem comes is when the milk and the cheese and the yogurt, which once came from the dairy cows that graze on grass, now typically come from hosting that spend their working lives forced to eat corn. And that can upset their stomach. Cows are ruminants. They eat grass. But they have bacteria in the stomach to help them digest grass, but we force them to eat corn. And this can lead to health problems. Unlike dairy cows, which pay for their room and board. Some of you here are students, you know you have to pay rent, you have to eat. So, dairy cows, what they do is they pay for their room and board with milk and carbs. But cattle raised for meat are freeloaders until they are sold. And because of that, we want them to grow fast. So we feed them hormones, we give them antibiotics. And there's a known trick that adding low doses of antibiotics to animal feed can actually fatten just about anything, any of the livestock, from poultry to swine to cattle. And this is not to mention the other zoonotic threats to farmers that Professor Muller was talking about. So this is a slide to show you that usually people talk about you are what you eat. So I blame it on the chicken that I'm growing fat, because actually I was much skinnier several years ago. But actually now it becomes you are what you eat eats. So I blame it on the chicken blames on the food that is being fed. And this is what's happening to our whole society now. That's why people are getting obese. So industrial food essentially is going from chicken to the chicken McNuggets, if you agree with me. So we are just like cows, okay? If we change our diet, it's going to change what is in our stomach, the gut bacteria itself. So we do not have all the enzymes in our stomach to absorb all the food that we consume, but microbes assist us. Similarly for the cows, when you change the diet from grass to corn, that can make them very unhappy, or their stomach very unhappy. Family. So this brings us to the microbiome itself. I know that there's going to be a lecture soon here about microbiome. So we each carry about 100 trillion microbial cells, 3 million bacterial genes cells. And this is what it is. The human microbiome, all of the microbes genes can be considered as a counterpart to the human genome, all of our genes. So it's a counterpart. And this is precisely what we have. The importance of the microbiome. You see, 90% of all our disease can be traced to in some way back to the gut and the health of the microbiome in our stomach. And we have about 110 to 100 trillion symbiotic microbial cells in each of us. And then we have about more than 10,000 numbers of different microbe species in our body. And this is 10 times what we have ourselves. So this is 100 to 1 in terms of genes. The genes in our microbiome outnumber the gene that we have in our genome itself by 100 to 1. So there are 3.3 million non-redundant genes in the human gut itself. The reason that I bring this microbiome and compare with genome is for those people who will be working on the genome projects, actually if you are working in bioinformatics, you can actually switch and go and work in microbiome itself. So here, the last slide is just, the last picture is just to show you that between two human beings, we are probably identical to one another 99.9% of the time. But in terms of microbiome, you'll see that it's very different. So you're going to see that right now there's a microbiome genome, a microbiome project going on. So if you extend microbiome research to environmental research, to agricultural, to biomedical areas, so this is what is going on right now. Thus, we see that people are doing microbial surveys, people are still doing bioinformatics and microbial research itself, meta-omics itself, meta-omics approaches, and community host interaction models. And here's the microbiome solutions that possibly that will come out from computer modeling itself. You can fix the health of endangered species with wildlife, with probiotics, ousting invasive species using certain bacteria, treating groundwater that has been tainted by pollution, environmental remediation, that's cleaning up, oil spills. Professor Craig will be talking more about this afterwards, I think. Helping agriculture feed more people without fertilizer by employing bacteria that can make the crop grow faster and more robust. And actually, itself, the United States government is now doing another project using plants, and this is what they do. Okay, we have pathway modification, resource allocation, and robustness in the environment, response and sensing using plants. Use plants to detect toxins in the environment. Now, this is my last slide I have. So over the last so many years since 1993, when I was still very young, I became a tenured professor when I was 29 years old at Florida State University. So I worked with students to form a company. It's called Euronics in 1993 to study resource allocation. And then in the year 1993, 1995, I started D-Train. Actually, at that point, D-Train was called Data Trains, even when data was not popular as yet. So eventually, I shortened it to D because it could mean DNA, disease, or even discovery. And then as more data came in, we formed GeneCore, and that company has been acquired. So most of these companies have either been merged with other bigger companies or they have been acquired. So now after the success of the Genome Project itself, you are going to see now there are a lot of other home projects going on. Metabolome, Connectomes, with something to do with the brain, Human Epigenome Project, and microbiome project that I was talking about. So this is a golden age of open data. Actually, time I talk exactly 30 minutes. Thank you. So if you have any questions.
Thank you so much, Prof.
Questions? Okay, good. I'll take questions.